Hello everybody, my name is Amin and in this video I'm going to talk about TCP lifecycle. What will happen once you initiate, you start the conversation, the session opens, and then data sharing and then termination. So we have three stages. We have establishing the connection, data sharing or conversation, and terminating that session. First, imagine that diagram. So we have one computer on one side, server on the other side, and then they want to talk. So I said, we need to talk. How it happens? Technically, we have something which is called a ladder diagram, which is like this. It ends up like a ladder, and it shows the flow of messages. The computer wants to start, initiates the conversation. So it sends a message towards the server. In the TCP header, TCP is a layer for protocol. In the TCP header, we have these items, and each item is responsible for something. We have source port, destination port, and the other things. And also we have some flags, which are responsible for specific things. We have urge, we have ACK, SYN, FIN, push, reset, but in our case, we're going to deal with only 3 of them. When you send the message, you turn, all of the flags are null by default. You turn SYN flag on, so you put 1 instead of null into SYN flag, and it is a message in the network, so it needs a sequence number, which is a random number generated by the client, the one who initiates, who generates the packet. So we have the sequence number, we have the SYN, and then you send that message, and there is a acknowledgement. It comes, whatever message you send, it is in the nature of TCP. So there's an acknowledgement, it comes. What does it mean? Return the acknowledgement flag to number 1, the first step. So the ACK flag instead of null is 1 right now. And we have a sequence number. It is a message in a network, so it needs its own sequence number. And also, how you're gonna let your audience know that you're responding the previous message. For each message, you're sending an acknowledgement. So you need to have an acknowledgement number. And how you do it, you grab the previous message sequence number, you add 1 to that, and you send it. So the previous sequence number plus 1 is the acknowledgement number. So in this way, the computer knows, okay, this is the acknowledgement for that specific message that just sent. So look at the header. We have the sequence number, we have the acknowledgement number, and we have the ACK. But let's go back here. The first message was SYN, that it sends to initiate. On the other hand, we have SYN ACK. What does it mean? In the nature of three-way handshake in TCP, the client, it says, hey, I want to establish a connection. And then when the server gets that, it responds with, okay, I got your message and I want to establish a conversation or a session with you. So it's like bi-directional. And if it doesn't happen, then they don't know if the session is started or they're going to start. So it's like a bi-directional. So it's a SYN ACK. So in fact, we need another flag on. So the SYN flag now is on, and it is the case. You have 2 flags on. And again, there's an acknowledgement since this is a message in the network, and acknowledgement flag is on. You have a sequence number. So this sequence number now is, so computer or the client, it sends its own first message. For the second message, it's the previous sequence number, and it adds 1 to that. If the previous sequence number was X, this sequence number is X plus 1. And you have the acknowledgement number, which you get the message you're acknowledging, you add 1 to that. So you have 4001, 7001. And woohoo, you have the connection, which is on. So now the session is established. So you're gonna send the messages. Okay, this is my first message. I have acknowledgement for your first message. You have the second message, acknowledgement, third, and so forth. It goes. What will happen if the second message doesn't deliver? So the one who is sending, it knows by the nature of the protocol TCP, each message, as we saw here, has an acknowledgement. So if I send this guy and the packet, the segment, it it gets lost for whatever reason, then I will wait for the acknowledgement. Okay, I didn't get the acknowledgement. Probably the message didn't deliver. So I'm gonna do what? Wait for that, announce the timeout, and I will resend the message. So this is the first case. Second, what if the acknowledgement doesn't deliver? So the server doesn't know what happened. It sent the acknowledgement already. But you as the user, you're like, okay, I waited, I didn't get the acknowledgement. So either the acknowledgement didn't deliver or my message didn't deliver like the previous case. I'm gonna do what? I'm gonna wait and I'm gonna resend my message. So even though you send the message, you resend it again and then you get the acknowledgement. Perfect. But it's gonna take forever if you want to do one message acknowledgement, one message acknowledgement, one message acknowledgement. There must be a way more optimized and faster. Is it? Yes, there's an optimized way. Let's look at that. I'm gonna say computer A and B, it's easier for the sake of conversation. So when it starts, the computer on the right side, it says, okay, you know what? I have a receiving window. And the receiving window is something again in the TCP header. So it puts in the TCP header, in the message that it sends, it's like, okay, you know what? Every time you're going to talk to me, I can handle up to that specific number, which in our case is like 64 kilobytes. So my receiving window is 64 kilobytes. And it puts that there, which is called also advertisement window or receiving window. So you're going to say, this is my window size. Once you send it, you say, okay, this is my receiving window, and do not send me more than that before you receive an acknowledgement on my end, okay? And computer A will be like, okay, I won't. I'm just going to stick to what you are telling me. And also computer A has a receiving window as well. It tells to the computer B as well, my receiving window size is this number as well. Then computer A, it sets its sending window to the number that just got it from B. So, okay, I'm gonna put my sending window to 64K and I'm gonna send. So let's say each segment that you're sending is 1 kilobyte. So you start from byte number 1 to 1000. Here, the sequence number is the first byte that you're sending. So the sequence number is number 1. Then you go for the next byte, 1001 to 2000. Your sequence number is 1001. The third one, 2001 to 3000, sequence number is 2001. And then 3001 to 4000, and then 3000. Like that, it goes and it goes and it goes and it goes once you're done. So 63,001 to 64,000 bytes. You're going to send them and your sequence number is 63.1. So what will happen? You stop. You stop and wait. You stop and wait for what? For the acknowledgement based on the agreement. And then you receive the acknowledgement. So the acknowledgement number is 64,001. And what does it mean? It is, so computer B is saying, you know what, whatever you sent me, I got all of them, and now I am expecting to get this number, or this is the first byte that you're gonna send me, or this is the first sequence number of the message that you're gonna send me. Since computer B is telling me I'm expecting that, it is an expectational acknowledgement. And then, okay, I'm gonna wait for that, and then computer A, it sets the sending window to the next 64K, and then it starts the conversation and it sends and it sends. So this process is called stop and wait. So you send like a bulk of data based on the previous agreement on the receiving window size, and then you stop, wait, acknowledgement, next, and stop, wait, acknowledgement, next. So this is the stop and wait protocol. So if you compare by sending one message, one acknowledgement like that, your ladder, it takes forever to be built. Okay, but still, do we have an improvement on that? I would say yes. There is something which is called TCP sliding windows mechanism. What does that one mean? So it's a process to do the flow control. Maybe you can change things dynamically. And how? Let's see. Okay, now we have this. We have this new diagram. And we have some numbers on top. These numbers are representatives of the receiving windows. So when computer A, it says, I have 64K receiving window, it means I have 64K of these numbers. And for sake of the simplicity, we're going to consider each one 1 kilobyte. Okay, you know what? My receiving window size, I'm advertising that it's 64K bytes, which is fine. And then computer A, it's going to be, okay, I won't send you more than that before receiving an acknowledgement. And I'm going to set my sending window to 64K so far. Then you see, those first 64 numbers are highlighted, and they are the sending window from the side of the computer A. It sends the first 2 messages. So from 1 to 1000, from 1001 to 2000, they're already sent. In the meanwhile, computer B, it has maybe it had time, it opened up some buffers or generator, and you know what? It's going to send a message, like an acknowledgement like this to the computer, and said, okay, every 2 segments that you send to me, I can send you an acknowledgement. So I'm going to send you an acknowledgement 2001. So I'm expecting to receive 2001. In the meanwhile, since that message, it came during the conversation, what will happen? Computer A, it slides the window 2 more windows to the right side. So now my sending window, it's changed to 66 instead of 64, which it was initially. And then 2001 to 3000, 3001 to 4000, and as computer B promised, it sends another acknowledgement 4001. And computer A, what it does, again, it slides the window to the right for 2 more. And then it's going to be 64 to 66, 68, and then the conversation and acknowledgement, and it goes on and on and on to communicate the data. So this is how dynamically everything can go. And these acknowledgements also are called delayed acknowledgement. So this is more optimized, this is faster, this is way better so far. But you know what? While I was explaining, we're all talking about sending a message, receiving, sending, receiving. What if we lose a message? What if it gets lost for whatever reason? Then if it doesn't deliver, what we're going to do? Let's deal with that case. And I'm going to make it super simple. Receiving window, both sides are only 4, and we have 4 windows occupied to send. Computer A, it sends the first 4 messages. Computer B, it sends an acknowledgement for message number 1. And then once computer A, it receives, it slides the window 1 more towards right. And okay, I have the opportunity to send more. Message number 5, acknowledgement for number 2 in the meanwhile. The window, it pushes again or slides to the right. And then this one, number 6, and okay, the acknowledgement for number 3, the message number 3, it doesn't deliver. We have a packet loss situation. Okay, then the computer A, it's waiting for the situation to see what is happening. In the meanwhile, computer B, since it's in the flow of conversation, even it has the time to just keep on sending acknowledgement. So it sends acknowledgement for number 4, 5, 6, but computer A is expecting acknowledgement for message number 3. So it's going to be like, okay, I didn't get the message that I was expecting. So I'm going to call a timeout, and I'm going to check again. The start of the window is number 3, and I'm expecting that. And you know what? I'm going to go back to that number. So this one is called go back in. It goes back to the number that it was waiting for that, or it's the start of the window, and it sends again all of those messages like that. So this algorithm, it's called go back in. So it goes back to the message it was expecting to receive an acknowledgement. This is the first one. Second one, the first 4 messages they deliver: acknowledgement number 1, sliding window number 5, acknowledgement number 2, sliding window, message number 6. So far the case is similar. Computer A, it waits, okay, is something going to happen? And in the meanwhile, acknowledgement 4, 5, 6, they're all delivered. But computer is expecting number 3, and it's going to be, okay, we have a packet loss probably. Acknowledgement number 3, it didn't deliver. Either the acknowledgement didn't deliver or my message. Something happened with packet number 3 or segment number 3. What I'm going to do, I'm going to resend the one which is missing. So I'm going to send only number 3. And once it receives the acknowledgement for message number 3, it already has the acknowledgement for 4, 5, and 6. And it just slides the window to the right and it sends message number 7. So this one is called selective repeat, and it sends the message. So we have the go back in and selective repeat in case of a packet loss, segment loss, or data loss in sliding window. But we're talking about again the conversation between point A and point B. There is something else that we should add, we should invite to the show: the network condition. If we have a wireless link, do we have interference? Is the network stable? So sometimes we need to deal with the flow control. We don't, TCP does it for us. How TCP does what it does? What is TCP flow control situation? So let's go back. We have computer A, computer B. Computer A, it's going to be, okay, my receiving window size is 64 kilobytes, don't send me more. And computer A, it's going to be, okay, my assumptions, let's set them. The receiving window size, it's 64 kilobytes, which is okay, I like that. But let's see what is the network condition. There is an algorithm, which is mathematics, and it checks, it does some formula, and it's going to be, okay, based on what I see, signal to noise ratio, interference, and all of those stuff, modulation and coding, the congestion window and how your network is congested, like the amount of traffic, it doesn't sound promising to me to go with 64. The network congestion is 16 kilobytes. So you know what? I'm gonna put them into that formula. I would say minimum of RND and CND. I'm gonna settle for less. And then, you know what? I will send up to 16 because it's my congestion window. And it sends all of them. Once it receives the acknowledgement, again, computer B says, okay, I received that, but my receiving window is 64K. And again, it checks, okay, the receiving window on the other end is 64K. The network condition now is better. We have some improvements. So we can put it up to 32 kilobytes. And let's communicate with that. Between these two, 64 and 32, lesser of 2 is 32. So I'm going to send up to 32, and I'll let computer B know that I'm going to send up to 32. So it sends, it receives the acknowledgement. Now the situation is better. And then, okay, I sent you the acknowledgement, but you know what happened? I'm busy now. I cannot deal with that 64 that I was telling you before. So now in this case, the receiving window size of the client B is changed. Okay, then no matter how excellent our network is, it's gonna be like, lesser of 2, I'm gonna go with 8 kilobytes. Then it sends that number and it goes again on and on. And that is perfect. Now we know how the conversation has got started initially, all of the flags and like the window size, TCP header, what happened in the meanwhile, data sharings, acknowledgements, sequence number, and the conversation is over right now. So what do we need? We need to terminate the process. Okay, let me change this one. Termination. This is what we need. We need to terminate and just close the session that we just started. I'm going to just make it easy. Let's go back to the TCP header. We have the acknowledgement and fin, which is finish. Send was synchronization, fin is finish, and you're going to finish the conversation, right? So this is what you want. Let's call it session termination. The computer B, no matter who has started the conversation, we just consider like 2 points A and B, it sends like a fin message. So the fin flag is on, it's 1 instead of null, and it's a sequence number. Once computer B, it says, okay, I'm gonna terminate, I'm gonna finish this conversation. Computer B cannot send any more data, but it receives, still can receive. Then computer A, it's gonna send an acknowledgement, the same concept, the previous message sequence number +1, but it sends the acknowledgement. If there is any buffer or something, it sends in the meanwhile. This is why, like when we were creating the conversation, we had the SYN-ACK together. But here there is a waiting time. So the fin message, it comes a little later. All of the buffers, they go, and then, okay, computer A doesn't send any message, and then the acknowledgement, previous sequence number +1, and that's it. Done. The conversation is over. And also this video. And this is what I wanted to explain about TCP lifecycle, flow control, and everything. I hope you liked the video and you found it useful. Just, yeah, show me a thumbs up if you like that. And if there's any question, just put it in the comment below. Thank you. Bye.